Hi guys, here we are back for the first part of 11.3. Now that we have the first two sections behind us, I wanted to pause, do a recap, and kind of give you some context about what this chapter is really about. Now that we've seen a couple of the sections, it'll be easier to get an overview of just what we're going to be doing in the chapter. So there you see, I've written chapter 11 as sequences and series, and it's a bit misleading. If it was up to me, I would simply title this chapter series, or maybe infinite series. When you call it sequences and series, it almost feels like, well, like maybe half the discussion is sequences, the other half is series, and that's not the true, as you can see. We just spend the one section on sequences, and we spend 10 sections on series. So really the sequences is just to set the stage so we can then talk really about series. That's what this conversation is all about in the end. It's a long chapter and it's pretty dense, as you've probably gotten the idea already. So we're not going to have one test to cover all 11 sections. I'm actually going to stop. A natural stopping point is 11.9. So we're going to do everything up to 11.9. That's exam 3. Exam 4 will include 11.10, 11.11, and then all of chapter 10. We actually go out of order. And chapter 10 is a little bit shorter, so that works out well. Okay, so I wanted to, again, recap, give you an overall picture of what is going on. So here's my recap for 11.1 in these two lines. So when in our discussion on sequences, we really talked about one thing. At the end of the day, does a sequence converge or diverge is the big question. We're going to carry that same question when we talk about series. Does a series converge or diverge? But we did it for sequences too, and the way we do it is, well, we take the limit of the nth term as n goes to infinity. And if we get a finite number, then it converges. If we get infinity or negative infinity, or maybe even does not exist, then it diverges. Okay, very nice. In 11.2, we saw several things. So in our series intro, we were introduced to the nth partial sum of a series, and we called it capital S sub n. So what the nth partial sum allows us to do, you're not summing all infinitely many terms. You're only summing n of them. So sometimes that's like 10 or 100 or however many terms you like. The whole point of looking at the nth partial sum was because now we can look at perhaps what all infinitely many terms really add up to. So this is how we represent a series in general. So it has an nth term, the summation symbol, the sigma, because we're adding terms. And in general, you see it as, they say it started n equals 1 and then goes to infinity. Well, they're all going to go to infinity for us, but they might change their starting position. The default, the go-to is n equals 1 in general. So we saw, hey, if I know the nth partial sum, if I can describe the nth partial sum in terms of n, which is no easy task usually, and then I take the limit as n goes to infinity, that limit's going to equal what we call S, which is what all of these terms are adding up to. Okay. So we kind of had that perspective. So it turns out as the chapter goes on, we're usually not going to be able to find out what S actually is, what number those all add up to. And I said before, usually the question is going to be simpler. It's going to simply be, does that converge or diverge? But this is how we introduced it. If we can find that formula and take that limit for the nth partial sum, then we've got it. There's actually only two cases where we can find that value, and we saw them both in 11.2. I'll tell you what they are before we're done with this intro. Okay, so what's happening? Where do we go from there? All right, so we kind of played around with this for an example or two. We found that formula. Turns out that formula, a formula for S is right there for us if we know we're looking at number one, the first test we learned, the geometric series test. If a series takes this form we found, then we know a lot about it. So a couple things to notice. Well, it's a r to the nth power. There's your geometric. R is the ratio of one term to the next. You keep multiplying by r to get bigger or smaller. One big thing is that it always begins at n equals 0. That's the way the geometric series is defined. So if it takes exactly this form, then we know, hey, if the ratio, the common ratio, r is the absolute value is less than 1, then we can immediately say that our series converges. And in fact, we know exactly what it converges to. There's this nice formula, S equals A over 1 minus R. If r is greater than or equal to 1, the absolute value, then the terms are just getting bigger and bigger and bigger, and the series will diverge as we keep adding numbers. It'll either go to infinity or negative infinity. So there is the geometric series test. What came next? We learned two other tests. Next up was, sorry if I'm going a little bit too quickly for you to write, but this is meant to just be a recap. Next is the divergence test. So now we aren't noting any particular form. We just say A sub n here. It could be anything. And we say by default that n equals 1 in the description of the test. That could begin anywhere. Could begin at 0. N could begin at 2 or 3 or 4. By default, we say n equals 1. Okay, you get that. Here's the idea. If when we take the limit of that nth term, we get something that is anything other than 0. If that limit does not equal 0, then the series diverges. What does that mean? In order for a series to converge, those terms have to be getting smaller, and they have to be getting smaller all the way down to 0. Otherwise, when we are adding them up, we know it's going to add up to infinity or negative infinity. So if when we take that limit we don't get 0, then they're adding up to infinity or negative infinity, we know it diverges. One thing to really, really be careful of in the divergence test is if when you take that limit and it does equal 0, then we don't know anything. It might still diverge. And that seems, if you're really thinking about it at this point and you've got a good understanding of how these work, then it seems like, how is that possible? How could the terms be headed towards 0, yet the series still diverges? We're going to see an example of that in 11.3 where that happens. So, pretty interesting case, actually. A simple one, though. Nothing complicated. Okay, anyway, that's the point. Point is the divergence test. Finally, we learned about the telescoping series test. I can probably just keep this all on the screen. That was the third test we learned. Telescoping series test, I don't have any more notes on it. You really have to learn it through an example. I just want to put it here, because we're recapping everything. Telescoping series test is the other test where we can know what the sum of the series is. So we can know S because as part of the telescoping series, you end up taking the limit of the nth partial sum. That's just part of the nature of going through the steps in the telescoping series test. So you can know it for telescoping series, you can know it for the geometric series test, you know what S is. Those are the only two types of series where we're actually going to find out what all of those terms add up to, which is pretty cool. Clearly for a divergence test, they're going to add up to infinity or negative infinity. I mean, I guess you could say we know it there. But for converging, series. It's only the telescoping series and the geometric series where we're going to know what they add up to. And of course, we talk about the unusual ones right before, at the beginning, right? And then we get to the more mainstream, like kind of typical question. Simply, does a series converge or diverge? Okay, I'm going to stop this video here. We're going to begin 11.3 next.